Let's do one more example. So again, we have a 3 by 3 matrix A. We want to find the eigenvalues of A, and we want to find a basis for the eigenspace for each eigenvalue, just like in the past couple of examples. So as whenever we are looking for eigenvalues, eigenvectors, the equation that we want those eigenvalues and eigenvectors to satisfy is this equation here. But as we've seen, that is equivalent to satisfying the homogeneous equation a minus lambda I times vector x equals 0. We want this to have non-trivial solutions, and that only happens when we satisfy the characteristic equation, determinant of the coefficient matrix a minus lambda I equals 0. Okay, we need this matrix to be singular. So this characteristic equation is how we find our eigenvalues. All right, so let's solve this characteristic equation. So matrix A is the matrix 1, 0, 0, 1, 2, 0, 1, 1, 1. And then minus lambda I, that's just the identity matrix, but since I'm multiplying by lambda, it's lambdas down the main diagonal instead of ones. So if I do the matrix subtraction, I get 1 minus lambda, 0, 0, 1, 2 minus lambda, 0, 1, 1, 1 minus lambda. Now notice this is actually going to be real nice to take the determinant of because it is a triangular matrix. Right? It's lower triangular. Everything above the main diagonal is 0. And so because of that, to take the determinant, all I need to do is multiply the entries along the main diagonal. So 1 minus lambda times 2 minus lambda times 1 minus lambda equals 0. Okay, so that's 1 minus lambda squared times 2 minus lambda equals 0. And so we could solve this real easy. One solution is going to be lambda equals 1. The other solution is lambda equals 2. Okay, that's because this is already factored for us. Makes it super easy to find those values of lambda. All right, so in this case, we have two different eigenvalues. Lambda equals 1, lambda equals 2. Notice that means that a matrix, a 3 by 3 matrix, for example, will not always have the same number of eigenvalues as its dimension. Okay? This matrix is a 3 by 3 matrix, but only has 2 eigenvalues, not 3. Okay, so we have the eigenvalues. Now what we need to do is plug back into the homogeneous equation for each eigenvalue and solve. That will give us the eigenspace associated with that eigenvalue. So let's plug in 1 first. So if I plug in 1, so that's a minus lambda I times x equals 0. And in place of lambda, we have 1. Okay? So matrix A was 1, 0, 0, 0, sorry, 1, 2, 0, 1, 1, 1. 1 times the identity matrix is just the identity matrix. 1's down the main diagonal, 0's everywhere else. Do the matrix subtraction. I'll get 0, 0, 0, 1, 1, 0, 1, 1, 0. And this one's simple enough that you could probably find the reduced row echelon form in your head. The reduced row echelon form of this is going to be 1, 1, 0, 0, 0, 0, 0, 0, 0. And you could always plug it into the calculator if you're not sure. Okay, but obviously if I take negative 1 times row 2, add it to row 3 is gone, right? It's the same row. And then I could just swap row 1 and row 2. Okay, So that's a reduced row echelon form. Let me actually get rid of this. Okay. Notice I'm going to have two free variables, right? X2 and X3, both are going to correspond to free variables. Neither of them have a leading entry. So if I imagine the system with the zeros on the other side, X2 and X3 are both going to be free variables. Let's call them S and T. X1, I'm going to get 1x1 plus 1x2, so that's plus 1 times S, since x2 is equal to S, plus no x3s equals 0. And so x1 is going to be equal to negative S. And so my solution is x1, x2, x3 is equal to any vector that can be written in the form S times negative 1, 1, 0 plus T times 0, 0, 1. Okay. Notice then the eigenspace associated with eigenvalue 1 is equal to the span of two vectors. And so two vectors are going to make up the basis of my eigenspace. My eigenspace has dimension 2 in this case. So the basis is the vectors negative 1, 1, 0 and 0, 0, 1. That is a basis for the eigenspace for eigenvalue 1. Okay? We have one more to go. We need to find a basis for the eigenspace associated with lambda equals 2. So as before, plug 2 into lambda into the homogeneous equation. And then we want to solve this, so we need to figure out what my coefficient matrix here is. So matrix A was 1, 0, 0, 1, 2, 0, 1, 1, 1. And I'm going to subtract the matrix with 2 down the main diagonal, zeros everywhere else. And I'm going to get the matrix negative 1, 0, 0, 1, 0, 0, 1, 1, negative 1. So let's get this into reduced row echelon form. Okay, here I will use the calculator. So my matrix, first row is negative 1, 0, 0. Second row is 1, 0, 0. Third row is 1, 1, negative 1. Oops. And so there is my reduced row echelon form. 1, 0, 0, 0, 1, negative 1, 0, 0, 0. Okay, I can use that to solve the homogeneous system, and that will give me all the eigenvectors associated with the eigenvalue of lambda equals 2. Okay, so imagine my augmented part has zeros on this side. I do have one free variable, x3. Remember, whenever you're finding an eigenspace, whenever you're finding the eigenvectors associated with an eigenvalue, you expect at least one free variable. If you do not have a free variable, something's wrong. X2, we're going to get 1x2 minus 1 times x3, which is t, equals 0, which means x2 is equal to t. And finally, row 1, equation 1, I'll just get 1x1 equals 0. And so eigenvectors, the general form for eigenvectors associated with lambda equals 2 are some scalar multiple t times 0, 1, 1. And so the 2 eigenspace is the span of that one vector, 0, 1, 1. Which means the basis for this space, since that is clearly linearly independent, is 0, 1, 1. That forms a basis for this eigenspace.